What is up, guys? Doing the math over here, and today I'm going to be doing the MIT Integration B qualifying exam questions 1 through 5. Our first question is, find ln 2x over x ln x dx. So we see a 1 over x. That makes us want to perform a U substitution. U is equal to ln x. Well, you can't quite do that yet because we have an ln 2x. But luckily that's easy to resolve because we can split ln 2x as ln 2 plus ln x. Doing that, we get as follows. Now for the first integral, we can bring ln 2 out of the integrand because that's a constant. And we can rewrite as 1 over x ln x. And for the second one, we see that the x ln x's, ln x's cancel. So we're left with 1 over x. Now for the first integral, we perform a U substitution. Ln x is equal to u. Therefore, we have 1 over x dx is equal to du. So this can be written as ln 2 times 1 over u plus integral of 1 over x. So now this is pretty easy to do. Forgot the du here and the dx here, but still, 1 over u we know is ln u. So we have ln 2. Ln u, and u is, remember, ln x, so it's ln of ln x plus ln x plus c. This is our first answer over here. Our next question is, find the integral from 0 to infinity of 1 over e to the power of x plus 1. So the first thing we need to do is we need to add e to the power of x, subtract e to the power of x in the numerator, because there's no clever way to solve this right off the bat. So if we add e to the power of x, subtract e to the power of x, we actually get the integral from 0 to infinity of 1 minus the integral e to the power of x over e to the power of x plus 1 dx. Correct? So now we can just integrate this. The integral of 1 is obviously x. And then the integral of e to the power of x over e to the power of x plus 1 is minus ln of e to the power of x plus 1, right? Okay, so now if we just evaluate it with our bounds, we see we run into an error because it becomes indeterminate. Therefore, we have to express x in terms of ln. We know x is ln e to the power of x, right? So we can combine this to ln e to the power of x over e to the power of x plus 1, evaluated from 0 to infinity. Now we can easily do this. If we plug in like infinity, we get ln 1, which we know is 0, minus e to the power 0 over e to the power 0 plus 1. That's 1/2, so this is equal to minus ln 1/2. Bringing the minus to the power, we see this is ln 2. My third question is, hold on, my monitor froze up. Our third question is, find the integral e to the power of e of ln x times ln of x over x. So we see another 1 over x, which means we need to perform a U substitution. U is equal to ln x. Doing so, we get du is equal to 1 over x dx. So we have now that we have performed the U substitution, our bounds of integration change. We have ln of e, which is 1, and ln of e to the power of e, which is equal to e. And now this becomes u times ln u du. Now this is integration by parts, basically. We take ln u as the function we want to differentiate, and u as the function we want to integrate. So this becomes ln u times u squared over 2 minus integration of differentiation of ln u, which is 1 over u, times the integration of u is u squared over 2. This is equal to ln u times u squared over 2 minus, this becomes minus u, integration of u over 2. That becomes minus 1/2 times u squared over 2 minus u squared over 4. Remember, we evaluate this from bounds 1 to e. So plugging in e, we get ln e, which is 1, e squared, and then e squared over 2 minus e squared over 4. And now we need to subtract. Ln 1 goes to 0, so we don't care about that. So we have minus of negative 1/4. That becomes positive 1/4. So this is our answer. We can simplify it a little bit to e squared plus 1 over 4 plus c, or constant of integration. Well, never mind. It's definite, so we don't need the constant integration. Now this is our second to last problem. It is integral from 0 to 1. 0 to 1 of ln 1 plus x over 1 minus x dx, right? This becomes integral from 0 to 1 of ln x, ln 1 plus x, minus the integral from 0 to 1 ln 1 minus x. Make sure to put your dx's here. Next, we see that we can easily integrate both of these. All we have to do is perform simple U substitutions. For the first one, we have 1 plus x is equal to u. So we have dx is equal to du. And for the second one, we could put 1 minus x as v. So we have minus dx is equal to dv, or dx is equal to minus dv. So now doing that to our integrals, we have 0 to 1. Oh, I don't have a good eraser, sure. Since we've actually changed our bounds, it becomes 1 to 2 of ln u minus, so minus dx becomes a minus dv. We can change this to become a plus integral of 0 to 1 of ln v dv. I'll put du here. So now this becomes pretty easy to evaluate. It's just u ln u. Integral of ln u is u ln u minus u. Under the bound is 1 to 2 plus v ln v minus v under the bounds of 0 to 1. Evaluating this, we get 2 ln 2 minus 2. Minus 2 minus, this cancels out, of minus 1, that becomes plus 1. Next we do ln of 0. This tends to 0. Ln of 0 tends to 0, so 0 minus 0 minus, this cancels minus of minus 1, that becomes plus 1. This becomes 2 ln 2. We could simplify this by bringing 2 to the power, so this becomes ln 4. Okay, our final question. 1 second. My computer keeps on blanking. Okay, this is 1 over x squared plus x minus 1 squared dx. So the first thing we do here is we see an x minus 1 squared. We want to expand that. 1 over x squared. X minus 1 squared becomes x squared minus 2x plus 1. So adding that to x squared, we get 2x squared minus 2x plus 1. So now this will be super easy to integrate if we have a quadratic ax squared plus bx plus c, where a and b are either 1 or negative 1. So we can do that by taking a 1/2 out. This becomes 1 over, to leave our integral unchanged, this has to become x squared minus x plus 1/2, right? Now this is pretty straightforward, because now all we have to do is 1 over, this becomes x minus 1/2 squared plus 1/4. Now what we normally do is we have to let x minus 1/2 equal tangent at theta, and then we basically derive a new formula that the integral of 1 over x squared plus a squared is 1 over a tan inverse x over a plus c. So we can use that formula right over here. Using that formula, we have 1/2. So this is our 1/4 is a squared, so a is 1/2. So 1/2 1 over a, so 1 over 1/2 is 2. tan inverse x over a. Our x in place is x minus 1/2. Over 1/2, that becomes 2 times x minus 1/2. That's 2x minus 1. We can simplify this a little bit to tan inverse 2x minus 1. And then we add our constant of integration, and that's your answer. So I hope you enjoyed the first 5 problems of the MIT Integration Bee. Make sure you leave a like, subscribe, and I'll see you in the next video. Thank you for watching.